So, this is possibly the most unassuming title for a topic ever. It's not just graphing, it's harder graphing, okay? Now, let's just call that one that we've been graphing for a very, very long time. I want you to think about the families of functions that you know about graphing. Just call them out. Someone give me an example of a kind of graph that you know how to graph.
Parabola.
Okay, parabola, someone give me another one. Linear, okay, alright. I heard a third one over here. I'm going to, before I move on to that one, I heard linear and I heard parabolas. I'm actually going to lump them together into the same family of curves. And there's a few others that are in the same family. These are all polynomial functions, aren't they? So you told me about linear functions, degree 1. You told me about parabolas, which are degree 2. Then you can go cubics, quartics, quintics, etc. They're all the same. They are polynomial curves. These are the very first things that we learned how to graph. Okay, they were also the very first things we learned how to differentiate and find all of that funky stuff. I heard another one starting with H. Who said it over here? Hyperbolas, thank you very much. Hyperbolas are quite different. Polynomials have no discontinuities in them. And hyperbolas, they're kind of characterized by having those features and asymptotes and all that. Okay, they're two big families. What else can we draw?
Circles.
Circles, thank you very much. Circles are weird because unlike almost everything else that you can draw at the moment, circles are not even functions. What are they? They're what we call relations, right? You don't just have a single x value going to a single y value. You've got a single x value going into a pair of y values, generally speaking. Okay? Polynomials, hyperbolas, circles, exponentials. Now exponentials, they have a kind of twin brother, twin sister, which are log curves, right? I'm going to lump them together because they really are the same family of curve, the same family of graph, just looked at from opposing perspectives. What's the last one? So far, anyway. Think. They wave around a lot. We looked at them in complex numbers, trigonometric functions, right? These guys are pretty important. So this, more or less, excuse me, are all the kinds of functions, families of functions, that we've been looking at. Now I can, sneezes that don't come. I can add on to this absolute values. However, I hope you recognize that actually, absolute values are not a family of graph, are they? They're a thing that you do to other kinds of graphs. Does that make sense? And I'm going to come back to that point in a minute. So what does harder graphs include in it? Well, it doesn't include more families of graphs. What it's basically doing is taking these guys and exploring what it is to muck with them a little bit. And there are 4 different ways in which we explore that, okay? So the easiest one is what we would call geometric, and it's what we're gonna look at today, geometric transformations. Now I want you to think all the way back to year 7, when transformations was something that you learned to do with shapes, okay? There are 3 transformations actually that you learn to do with shapes. Do you remember what they are? Okay, I heard reflect, I heard rotate, and there's one more which sounds very similar to transform. Translate is the 3rd one, okay? Now each of these 3, what we said was important about them is that they change the shape in some way, but the size stays the same, and the features of the shape stay the same. So in other words, you get a congruent shape, okay? Now under graphs, the 2 of those 3 that we're going to focus on, and we're going to look at today, are reflection and translation. As it happens, with the kinds of things we know how to graph, rotation is actually surprisingly difficult to do. So we leave off it for now, okay? So geometric transformations. The second thing we learn about doing is about composing graphs. Now, what do I mean by composing? When you say, oh, this is composed of blah, 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 or here's a musical composition, or there's a musical composer. What does that mean? We often use it in musical context. We often use it as like, I'm going to compose a piece. That means I'm going to make a piece. Okay, but actually, composing a piece is made up of something that uses the word compose in a more general way. Like if I say a rock is composed of, right, or water, the chemical is composed of. What would you say?
Combining the individual elements.
Yeah. In fact, anytime you see like that suffix, right? Like co-interior or corresponding. It's when things are sort of jammed together, right? So when you are composing graphs, what I mean is, well, you could take any of these guys, and you could add them together, right? You could take a trig function and you could add it to, say, a linear curve, right? And you would get a new shape. You could add them together. You could subtract them. You could multiply them. You could. Okay, so all of these ways, all these functions over here, you can combine them. You can compose them in these variety of ways. That was the first two. The last two sort of hang together a little bit. We're also going to look at powers of functions, powers of graphs. So if you take one of these, right? Take, say, graph of an exponential, right? Or the graph of a polynomial. What happens if you take that whole thing and square the whole thing? Or cube the whole thing? Or apply a square root to the whole thing? Or take the reciprocal of the whole thing, which would be what power? If you took the reciprocal. Negative 1, okay? Like, what does 1 on sin x looks like? Look, we actually have a special name for 1 on sin x. What's it called? Coset. Right? So what does that look like? Now, I've explored some of these before, but does anyone know what 1 on log x looks like? Or 1 on x cubed? Actually, you can work that one up fairly easily. We're going to look at that for all these families of functions. The last one, and it's interesting, I may not do it last, we'll see, because it's actually very useful to extension 1, is a technique for understanding graphs better. And it's more broadly applicable than that too, but this is the first place you meet it, called implicit differentiation. Now, just as with many other things in the Extension 2 course, it is attempting to intimidate you just by its name. Nothing fancy, it's actually a special use of the chain rule. But it's something that comes into the context of, like, circles, right? Circles. What's the equation? Give me an example equation of a circle. Sure. Let's go, something like that, okay? Now, if I were to ask you to find the gradient of a curve, we know how to do that. We can do that in our sleep with our hands tied behind our back. But when you look at something like this, you're like, well, hold on a second. I don't like things written like this. I like things written like this. Equals and all the x's over there, all the x's over there, right? What do you do with this thing? Now you can, this thing. You can do a couple of things with it. One of the nicest way to deal with it is this thing called implicit differentiation. You want to know the gradient, but it's in this weirdo looking form, well, you can still work with that if you're happy to learn some new tools. Okay?